almost done, and we might fit one more of these in before the end of the year, at least for Vibecast. I'm going to be heading to Mexico, Playa de Carmen, just south of Cancun, next week for some time off. Wife Brenda tells me I'm not supposed to bring a laptop or I might be in trouble. So yeah, I do have separation anxiety from my laptop a little bit. We'll see. We'll see. Again, I'll have bigger separation anxiety if I bring the laptop and Bren's upset. So we'll let the lesser two evils there. Right. Yeah, so actually one sec, guys. I'm gonna just do the mute all. So when you're if you want to talk, just unmute yourselves, but this is the one that doesn't auto mute, so I'm gonna do that. Yeah, it's been a week of sorts. I'm trying to put it all together. With you probably saw the Linux Foundation, which decided to do the Agentix Foundation. And what was interesting that I found out about this basically on the way to the meetup on Tuesday night here in Toronto, which put me in a kind of weird headspace to say the least. And when I was like in high school, I was a nerd. I started the computer club. I like to start clubs, as you guys probably can tell. So the internet became a thing when I was in about grade 11. And I started the internet club and all these things, but I was never really like, I was in the drama club as the AV guy, stuff like that. So you can tell I was a nerd. And when it came to sports and gym, I was always like the last guy chosen because, I'm not exactly going to be the guy in your basketball team. And all I could think of when the Linux Foundation sort of comes out and says, we got 500 of the biggest agentics companies on the planet and never bothered to call Rube, I felt like, oh my God, it's like grade 11 and I'm not being chosen for the basketball team again. But I'm trying to deal with it best I can. But to be honest, the support that came up, I guess through this weird week that we've had, the support of you guys and everyone that's we've sort of surrounded ourselves that sort of empower us through difficult times has been really rewarding and actually ended up feeling really good. And I really do appreciate all that, all the comments and all the messages and everything that everyone's done. It's, this is why we do this. It's this camaraderie. It's the when I say I never leave the office, I do. I leave the office every day and I get to interact with you guys and I get to feel good and we pick each other up. And that's, agentics aside, we're humans and we have emotions and we don't like being not picked for the basketball team, right? It feels bad. And you guys made me feel better. And I really do. I think thank you for that. That's all I want to say. So, all right, enough of that. I don't want to dwell on that. Who cares about them? So, what's new, Rob? What's happening?
Well, it just seems like so much stuff going on just as it's crescendoing towards the end of the year. So it's really wonderful. The hackathon was an enormous ton of fun over the 3 days. Kudos to the Paris team and to all the folks that piled into the Kaltura and the Discord over the course of the weekend. Just like a ton of different ideas and different ways to come at it. So we're all just digesting all the plethora of features to pull them all together into that final presentation for the supporters and for TV5 Mod. Our Saint Jean Marie, Vincent, and of course, everybody else that was knee deep all weekend. There was a lot of folks like Nick, you, Monduip, Nolan, Matt, just were in there as moderators too. So pretty much almost any time of day, folks can come in and roll through. It was really a neat experience. So yeah,
Yeah,
that was quite the weekend.
some of the highlights, Alexandro and Nick and Colby, and we're like, I think it was
Yep.
like, what was it, like midnight? We're just blabbing about just the most random things. Kobe apparently decided to like unravel the mysteries of the universe, and he's convinced he has. I don't know if he has or hasn't, but his excitement around his discoveries is like, for all intents and purposes, he has unraveled the mysteries of the universe, in a quadrillion times a second or something, right? It's I think we need to spend more time hanging out on these like dis I think we should do Discord. It's a little easier. It's kind of meant for that. It sends a blast out to everyone that's
Sage. Yep.
yeah. So maybe let's try to do that more. And
Yeah.
yeah, well maybe and I'm always up at 2 o'clock in the morning building crazy things. So maybe we can find someone else who's just as crazy. Uh Nick, how's it going?
Good. I'm just working away on my LM DevOps ecosystem, working on the infra, or actually the integrations components to it. So I'm getting like all the LLMs baked in, some of Roove's toys baked in, and some communication tools. So, the system can be smart to talking to Slack and people can talk back to it and things like that. So yeah, just kind of wiring that up, and then I'm working on the simulation component of it. Originally, it was really just to demonstrate the system, and then Reuven came out with this like crazy thing that simulates all the activities of entire business. So I'm basically just I'm actually cooking that in. So it's actually going to show all the LLM activity across a company. It could be the size of like IBM or something, and then it'll actually show a simulation of the system working with that. So it's evolving quickly, and yeah, it's pretty sweet.
We did a simulation. Was it? So much stuff happening right now. Over the weekend, as part of the hackathon, just on a random whim, of every voting person in the United States, just because that seemed like the place to start. And then we did. What was the number that he mentioned? It was like some astronomically large number that we did of simulations of every possible direction based on external factors that an individual might do within a certain jurisdiction. So I think the voting population in the U.S. is like 150 million or something. Basically, half the U.S. can vote or something. I don't know exactly the numbers, but and essentially, then the system is like, hey, let's figure out what their political affiliation is, what their demographic profile is, what they likely voted in the last, based on sort of factors that indicate voting habits, and then let's run that millions and millions of times per each and every individual in the United States and see what happens. And I think he did for the upcoming midterm elections. Needless to say, according to this, it's not looking good for a certain party, but I guess we'll see what that looks like. But it's still, I think it came out being like 1.5% to a difference between the sort of overall public vote in the U.S. So interesting. We'll see what happens next November. Maybe we'll record this and come back and see if how well our prediction system worked a year prior. So yeah, the simulation stuff's crazy. What else we got here? Michael O'Boyle, you sent some really interesting stuff to me on LinkedIn. The you see, we figure out. I'm gonna let you actually describe it. What did we figure out?
Well, I'm still wrapping my head around it myself, but we were able to take some of your technology for doing machine learning and other techniques and embed it into an iOS app. So I was able to uh, generate. This was in part for the hackathon. The angle I took was to build an iOS app. I can show some stuff once I get my stuff together here, but essentially keeping all of the information on the device was important to me. So I was taking health data, activity data, all sorts of the fun sort of accelerometer goodness that we get from our devices these days, and evaluating that to build a mood, and then trying to map that mood onto um, TV selections, movie recommendations. So you pick up your mood, and you look at you use that mood to sort of pick your movie. And what Roove's technology added, among other things, was the ability to sort of learn over time and kind of predict the mood. And so, kind of exploring that area a little bit more. But it was neat to basically take, Rust, convert it to, you had Rust code, convert it to WASM, and then we can kind of bake it into an iOS app. So good stuff.
It's so and it's two parts, and I know because we share all this stuff. It's in the root vector repo that I can show you guys. But basically, the it's a WASM, and you're going to hear about WASM a lot today because I'm actually using it. Most of the stuff I'm going to show you is using WASMs in two approaches. One is in the browser. I'm essentially borrowing the compute resources, potentially GPU network where I can access it, and from the client. So rather than having to go and make requests directly to a cloud somewhere, it stays all local. Now, what's cool about what Michael and I were working on is I can do that for two things on the iOS. I can access all the health, I can access mapping, I can access all the internal sort of SDK capabilities that are accessible, one through the browser, which is actually significant amount of things I can actually access. Then I can train and learn based on that. So I can learn, for example, based on health information, and then adapt and give you suggestions and understand what's happening. If you've got an Apple Watch, I can see some of your biometrics. None of that information leaves the device. It's all anonymous. So a couple things to know. And why is this important is specifically in the EU, there's a lot of things we can't do because of the GDPR, personal identifiable information and other things, as well as just, they don't want you sharing that level of information, especially stuff involving, things I mentioned about on your phone. So we can get all the benefits of a self-learning system without having to worry about the sort of EU getting all in our business because that data never leaves. And on the better bit, I'm using native access to the actual CPU and GPU capabilities on the phone. So I'm getting the SIMD, and these phones are smoking fast. I'm actually getting way better performance on a phone than I am on getting on my own computer because they're optimized for this type of environment. Just absolutely insane. So the second part, so that's the browser. The second part, we can pop these WASMs, again, it's a compiled version of a sort of standalone algorithm, and put those directly in the Swift code, and then they run natively in your sort of compiled Swift application as well. So you can use it on either scenario. So I'm going to show you the browser scenario here in a minute, but I think we're doing some crazy stuff here. Again, it's sometimes hard to sort of feel where the line between, am I delusional and is this something novel is hard to tell. But I think we've been doing some interesting stuff over the last couple weeks here. Before we get going, I know also, Martin, you've been working on a new video ask system. You want to give that a little demo quick? Did I lose Martin?
We got you
Oh,
muted.
sure.
There you go, Mark.
Yeah. Okay. Sure. I guess I could do that. So the point really was to we have a lot of people that have had a really positive experience with the Agentic Foundation. At the same time, suddenly there's all these announcements about organizations that really haven't been doing what we've been doing for as long as we've been doing it. So as we haven't collected that social proof, I was looking for a way to do that. And so I suggested a couple of days ago at I think a marketing event that we gather a few little videos where people could just say, this is the experience that they've had. If you want the full context of that conversation, I'm going to post a summary into the chat this came from Fireflies. I posted it back into posting the Discord, so you can look at the thing on Discord. And essentially, Video Ask is a platform where it has a tree, like a graph, and you can ask it a series of questions. People can give you video answers or they can type text back. I literally set it up 5 minutes before this meeting, so there is no text alternative at the moment. That's only because I didn't set it up, not because it can't do it. And so I set up 3 questions about the hackathon, and my request is that if you participated in the hackathon, that you take a couple of minutes now. Consider this a barn raising exercise. Right? So if you're barn raising, you basically say, well, we could all come and help you with your house at some point later at a random time. The chances are you're never going to do it. But if you've got a group of people together and you say, right now, we're each going to take 5 minutes or not even 5 minutes, because actually the prompt length is like 60 seconds a person. If we each take 60 seconds to go through these 3 questions and answer them or skip the question, then at the end of it, with 70 participants, we'd have over an hour's worth of footage, right? And that is actually a really powerful thing for the foundation to collect. And if this is an approach that works out well for us, well, maybe we don't use Video Ask in the future. But I kind of like Video Ask because it's configurable with webhooks. You can pay for it on a month-by-month basis. And yeah, so that's my ask. I have pasted the videoask.com URL in the chat. You will see a dialogue like this. And if everyone's cool with it, I would suggest you go and do it now, because there is no time like the present.
Yeah. Thanks, Martin. Looked great, and thanks for putting this together. I sometimes spend too much time on coding stuff and not enough time promoting stuff, I suppose. But this will help, I think, a lot.
Yeah.
All right. So we're gonna jump into a few things. Well, actually, let me just take a moment. Anybody have anything they want to say? Any opening comments? This is your quick moment here to if you
Just to
want to.
mention, maybe a new meetup for Argentic Foundation happening in Novi Sad next Tuesday, December 16th. So this will be in meetup number 4. Just a small update from, this side of the world.
Nice. And thanks again for putting all together. I wish I could go. Back in my cloud days, I went to all these events, and I ended up hitting 67, was it countries or cities? I think it was cities. 67 cities around the globe. But that was a long time ago. So I don't do that now. I never leave the house. But anyway, times change. And yeah, anyone else got anything? Here, Alexandro, I'm sure you were hacking on something here that some interesting things with Colby, and anyway, here we go. I'm going
let me
to
throw something out there, Reuven, just Dave.
Sure.
Just a quick thing. Some of you may have, sorry about the background noise. I'm in my favorite coffee shop. The Linux Foundation, OpenAI, Microsoft, AWS, and Anthropic all announced they announced the Agentic AI Foundation. So they're sharing very closely our name and I guess our thing. So I don't know if all of you guys have seen that, but there's a new foundation out there that's kind of copying or trying to emulate what we're doing here.
Yeah, emulation is the highest form of flattery, I guess. Yeah, I mentioned that earlier. It's unfortunate given the fact that they're open, and I think they're just at this point doing whatever they're going to do. They're the 800-pound gorilla. For now, we are the #1 spot on Agentics when you type it into Google. When that changes, I guess we'll have to work accordingly. But yeah, some of the folks have reached out. I will have a conversation, I suppose, when see what they have to say. And the folks who, other than the main dude, whoever that is, Mark something or other, everyone else over there has been very supportive. So I don't know. We'll see where it leads. I'm an easygoing guy. It's a little unfortunate, but I guess I'm kind of over it at this point. Yeah, that's all I can really say about it. What else can I say? Yeah, what am I gonna do? These guys are in 3.5 billion phones. All right.
We'll all shake out in the wash. Yeah.
Yeah. There we go. Let life give you lemons. You make an agentic system. Here we go. Okay, so we've got. I'm really into WASMs, and there's a couple reasons why I've been into WASMs. I've been working, as you guys know, on this chip, and it's a recurring conversation because I'm super excited about it. But a lot of the innovations that you're seeing are sort of straddling the line between the ability to embed complex capabilities directly in silica. Now, as you guys know, I kind of, I don't know if it's kind of won the lottery or what, but the crypto bros that are doing these chips, giving me the ability to sort of piggyback on their fab run, which normally would cost tens of millions of dollars, and I'm luckily able to do it for free. So thank you, my Norwegian friends. So what you're seeing here is two sides of what I'm learning and discovering, right? So I'm learning the sort of inner workings of the sort of ASIC chip structure, not RISC-V for those who are asking. This is custom silica, and the ability to do a kind of programmable modular WASM that I can then directly put on the silica and optimize for the capabilities of that chip. Now, the strange thing about working on these systems is they need to be super small. So all the things I'm showing you here in this web, so it needs to fit in 7 or under 8 kilobytes of space. So now just to think about 8 kilobytes, I got to create an AI system that operates in 8 kilobytes. That's roughly about how much you need to go when 1969 to the moon in terms of the software running that system, right? If I could go back in time, hypothetically, I could probably run this on a 1986, XT computer or a Commodore 64. I should probably try that actually. They're still available. But that's the size. So I'm working in kilobytes, right? So now I've got to take all this stuff, all these attention mechanisms and all these vector structures, hyperbolic systems, and pack them into a super tight, compact, quantized, package that I can put in this chip. Now, when you think about all the things that you've been seeing me do over the last couple of years, these neurosymbolic structure, which gives me a 98% shrinkage in size, and all these other things, they're all leading kind of to this moment where I get the ability to jump from the virtual to the physical. And I've always been, generally speaking, a software guy. So my space has always been, my comfort zone has always been building things that are malleable, software, right? And hardware is a whole different animal. But what's interesting, and you're probably seeing this over the last several months, as I explore hardware, I start exploring these sort of inner clock cycles of these TPUs and the cores and the different parts, the raceway components within these chips, and I start realizing that the true opportunity in these things are to create a kind of physical representation of the kind of neurological processes that happen within our own brains, right? Spiking neural networks, which we get a spike of energy, with the ability to have the interconnected relationship between the different cores, the ability to manage multiple cores that are far apart. Think of the ability to build a system that is capable of running in a light bulb, but all the light bulbs are now running in a kind of concurrent fashion. One light bulb goes out, the system can't go down. That QUIC protocol I've been so excited about, the UDP protocol, now makes complete sense. I can literally have a building full of light bulbs with these tiny little chips in them, each one acting as a 256 core neural network, all collaborating with every other light bulb in the building, and we now have a distributed, computing system that's nothing more than a bunch of light bulbs. That's the power of these systems. So what I'm doing here is creating a chip that thinks, that has the same sense, the same ability to think, the same ability to act, and the same ability to learn in loops. But I'm doing that super fast. I'm doing that 100 million times per second. And to be honest, I think we can get, if we start using this idea of sort of echo and sort of this kind of simulation within a simulation, we can get that number up many orders of magnitude further, potentially in the billions or more. And that's what's interesting. So when you start looking at this ability to create things that are working in nanoseconds, complete 3 to 5 cycles in 10 nanoseconds. I'm working essentially at the speed of light on a chip, which is mind-boggling for me, which is something like, if I'm just talking about 100 million queries, we're talking 4 million times faster than you think. So when you start thinking that I can operate 4 million times faster than you think, and this thing currently is a centimeter in size, imagine what this looks like when I'm at 2 nanometers, which would be a grain of sand. I can fit 256 cores in a grain of sand with technology available today. I just need $150 million to do it. But hypothetically, if I could find $150 million, you now have the ability to do all those things I just told you, but they're so small and run on so little energy, 0.03 watts. Your brain runs on 20 watts, that you can now look at attaching these and using these in parallel to your brain processes. I'm running 4 million times faster than you think, in a system capable of understanding, learning, and adapting to the very brain waves that exist within your head. Like bonkers, just absolutely craziness. And this is with technology today. This is going to fab in like a week or two, right? And we'll have the physical chips by March. So this is like, for a geek, this is like winning the lottery or something. So the system learns. It learns how you learn. So if you use it in conjunction with an industrial control system, it learns how that industrial control system works. If you're putting it into a neural implant in your brain, it learns how you think. If you put it into a pacemaker, it understands how you beat. If you taking it further, because the system, it kind of learns based on the kind of intersection of a kind of wave function, a spiking neural network, and all these various parts, we can start thinking about the ability to repair nervous systems, right? Having the ability to understand the signals that are flowing through your unique nervous structure in your spine, and then providing a kind of bridge between what's broken and what exists, learning what it needs to do, all the while getting better, self-enforcement, and things that are the size of a grain of sand, which is, and again, sci-fi land, but totally doable. So here's a quick sort of traditional, and I'm not trying to, I'm actually going to give all you guys the first group of chips to play with, because these chips are dirt cheap. Like we're talking, I don't know what the end price will be. I'm sure they're going to force me to put a decent markup on it, but the core costs are like $10 to start. So even at $50 a chip, who cares, right? So we're looking at, and this is this little presentation you guys are, I'm giving you my first presentation. Why not? So we're talking 256 little brains, not one. WebAssembly. Now the WebAssembly, and you're going to see this here in a minute, the WebAssembly is the most interesting part of the whole equation, because we've included the WebAssembly on the chip, we can repurpose the chip with, assuming you have the correct key, that the key is based on the cryptography of the defects in the silica of the chip itself. So the imperfections of the chip is the entropy needed for the actual encryption on the chip. So each chip is unique. It has a unique cryptographic signature based on basically its imperfections, which is also crazy.
But doesn't that mean if the chip's imperfections can be encoded as a private key, that chip suddenly can be simulated or mocked elsewhere?
Yeah, that hypothetically, yes, but that would require astronomical amount of effort to do. Maybe the US government or someone can do a microscopic analysis or something and try to recreate the structure of the chip and so on. Yeah, maybe, but
use 9 chips to decode the 10th.
The imperfections are random. The ability to do that would require beyond the computation of every computer on the planet working in unison kind of thing. It's really hard to do. Now, I'm not saying
this is exactly what quantum computing can do easily. Quantum computing can break keys. They can reverse engineer keys. That's the great advantage.
Well, so as you guys know, I did QDAG right a while back, which is a quantum resistant architecture. So what I did is I took, these are the NIST quantum resistant algorithms. Now, I'm not saying they're quantum proof, but they're quantum resistant. So what you're doing is you're using a combination of these quantum resistant algorithms from the NIST organization, along with the random imperfections within the silica. It's ridiculously difficult, well beyond the capabilities of any quantum computer that exists today, and probably for quite a while. Now, as the technology adapts, because I've got a WASM, I can just update the algorithm on the fly, and nothing is impenetrable. I'm not claiming it's an unhackable chip. It's just really difficult to do. All right, so the system learns while running. So it basically I create this neural network that fires together and so no back propagation required. The chip adapts to new patterns without retraining. It learns the patterns it's adjacent to, so basically all you need to be is basically sending it information, and it kind of just discovers what that information means, and then creates simulations and basically attention on those things. So because it's doing that on the chip, you get nanosecond decisions. So in my tests, and this is just using a CPU, by the way, SIMD, and in my tests, we're seeing 50 nanosecond think sort of loops. You know, this idea of the causal loops that I'm so into, right on the chip. So we're talking 3 to 5, 3 to 5 cycles every 10 to 50 nanoseconds, which is just an infinitely small sort of range. The other thing I put on here, and as far as I know, this is the first and only, everything you see here is the first and only for any of these chips. I don't know any of them that do this. The next really exciting part of this is the idea of embedding the core NSSW algorithm right on the chip. So, you know, the pathfinding algorithm that's super fast for vectors. So it's RAG optimized. So basically you plug this thing into, you know, my root vector or whatever, and suddenly the thing's a billion times faster and smarter. And all you need to do is pop it in your thumb drive kind of thing. It also has hyperbolic structures. So rather than a Euclidean sort of flat plane, which is the traditional vector, this uses that universe model I love so much, right? It's a circular sort of infinitely expanding sort of globe structure. You've got the vector, the latent space, and you got the implementation of the graph. I've put the graph also in the chip. So you've got direct attention, you've got memory isolation, it works on like a battery. And this is all real, just incredible. So let's go a little further here. So I've got a toolbox. This is the part's a little techie. I don't know. This is just my presentation. I'm sure the guys doing the actual marketing will do their own less geeky version. But in this particular scenario, you've got different math. So a lot of the AI that you're seeing me do is based on mathematical principles, right? I'm taking the concepts of strange loops, you know, this looping effect that happens on sort of sub-millisecond basis. Then I'm applying different forms of mathematics to allow it to understand. And then I'm using mathematical tricks to sort of optimize the process of how it does the math, right? So it's all essentially various forms of mathematics, novel mathematics, and that tries to solve and use it to learn and do. Then we've got this idea of leaky activation, which I kind of liked. And this, again, getting kind of geeky here, but it's for deep networks that train faster without dead neurons, blocking gradient flows. One of the problems you have with GPUs is this idea of dead neurons. You're blasting all this information, all this electricity and energy really fast, right? And you can illuminate an entire town all at once, but you're blinded by that light and you can't really see anything in particular, but you kind of see the entire city, but you don't really see the particulars in a corner somewhere, right? So what this does is basically does the opposite. This is surgical. I'm firing a specific bit of electricity at a specific neural process or core in the system for a moment to do that thing, but I'm doing it really, really fast, nanoseconds. And then I'm looking at something else. I'm simulating, I'm learning, I'm adapting, I'm doing that really fast. And within, a second, I've done that billions of times potentially. So this is doing that directly on the chip. Then I'm able to do decisions because I've now infused the system with attention. So the attention itself exists within the WASM, which you'll see here in a moment. And that allows the system to then go and say, what's meaningful? What matters? What should I do? Why does it matter? So it's the idea of logic, understanding, comprehension, and reasoning. Again, as a mathematical principle, not as a what's the most probable next word. That said, I can use the micro LoRa structure to actually train, using this chip, a sort of hyper optimized version of a language model as the system is interacting with it. So there's so many interesting use cases. It's crazy.
Is the hardware memory volatile or non-volatile?
Sorry, say that again?
Is the hardware memory for this chip volatile or non-volatile?
Well, that's a question for Roger.
Use its value when it loses power.
That's a question for Roger. I don't have an answer to that. Don't know. Yeah, it's so I'm doing I'm handing
Medically, the chip lost power. So
I'm no
knowing how it's built up.
it has okay. So I do have the ability to resume. So there's obviously some form of memory that I have there. So it doesn't lose its state. It remembers where it's left off. So I'm not sure which way that answers your question, but that might be helpful. All right. Next thing we got here, and these are all everything you're seeing in this stack here, this entire stack, 7.6 kilobytes. All these features. These are all the algorithms I quantized and made super small. So now you have where do I leave off here? Finding similar things. You got block distance. So these are all the vector structures. So I can in the same way I've done the Roux vector components where I've got the latent space and I've got the actual sort of graph implementation. I've packed that in as well. So you can use it for sort of fast traversal of complex vector space. So you can choose a variety of different sort of process. You get cosine, you get straight line, you get block distance and tree distance. Tree distance, I can comfortably say nobody's ever done this. Well, all this, I don't think anyone's done, but this is like sci-fi land. Like the fact that I can do hyperbolic on chip, like, and I think I've got Guy on the call. Guy, have you ever heard of that? Has anyone ever done this? I think he was on the call.
I have not heard anyone doing that yet on chip. So cool.
It's crazy, right? It's a little crazy.
Yep.
And the reason I mentioned Guy and I worked at Citrix, and you guys might have known about 10 years ago. And we wrote these series of papers. And well, actually, Guy wrote most of it. I just added a paragraph or two. But what was interesting about what Guy and I were discussing and writing about back then were a lot of these concepts, right? And what's weird is all the things Guy was telling me was going to happen. I'm like, and I think you somehow influenced me in the back of my brain. And now we're able to do those crazy things. And this is the first step to all those things you were envisioning, 10 years ago. Yeah, so last part here, we got spiking neural networks. And this is a really cool feature. So the spiking neural networks, and I think a lot of neural networks that we're going to be seeing over the next year or two are going to use the concepts of spiking neural. So the spiking, and I'm probably not doing a great job of explaining, but basically it's an event-driven system that sends information just to the thing it needs, illuminating that one particular process. So think of like agents, and I'm building this as an agentic system. They're spawning that agent, doing that simulation, it's understanding that thing, and then moving on. And the side effect of that is it takes an already really low power system. This is running essentially at 1.8 watts and amplifies the efficiency of that by an order of 100x. Now, that's really cool, even at a 12 nanometer scale. But what's really interesting about that is what that looks like back to the grain of sand capability. So that is essentially we have now, and I'm going to sound like a maniac, but I'm going to say it. We've created a synthetic neuron. Now it's not the size of neurons; it's the size of a grain of sand. But let's assume Moore's law applies, and every 5 years or whatever, there's a 10% reduction. So within our lifetime, we are potentially in a spot to have these things the size of cells. They can be cell adjacent, like literally, and using the power that exists within your body to power your cells. We can get smaller. We can embed these within every cell. What's interesting about that is when you have aging, which is a combination of DNA sort of mutations, I guess, and you get cell degradation based on those. When you can embed these things directly at that scale, you can repair those things almost instantaneously. You can have these adjacent to your white blood cells. You can have these adjacent to your gut bacteria. You can have these adjacent to to seek out cancerous cells and rewrite the programming on them so that they don't expand. You can do all kinds of other crazy sci-fi things in your brain. I can download a potential ability. I need to learn how to play guitar like Jimi Hendrix. Bam, I'm playing like Jimi Hendrix. I want to hit a baseball like someone that didn't do a whole bunch of steroids. I don't even know who that would be. You can do that, right? It's crazy the things you can think about. So all those things back to the sort of matrix, download the ability to do karate and various forms of kung fu instantaneous. It really starts looking at this kind of idea of transhumanism, right? You take that step further. You've now broken, there's a barrier to how small these things can get, right? You're never going to get past the sort of atomic wall. You're not going to enter the quantum realm like some weird movie. But at a certain point, you are going to be small enough to fit into a single DNA. You could hypothetically, and I'm getting off in the weeds, whether it's 40 years or 100 years, I have no idea. But at some point in the future, if the current level of shrinking continues at the level it's doing right now, in roughly 50 years, 50 to 60 years, so possibly within our lifetime, definitely within some of the younger folks on the call's lifetime, the ability to have these things directly in your DNA, rewriting and repairing broken or mutated changes to your DNA in essentially real time. Which then, if you want to go well into the deep end, means potential limitless life, or the complete augmentation of what it even means to be human, which is even crazier. But that's 60 years off in the future. All right, last part. This is memory gateway. So yeah, this is the chip, and I might be going into crazy land. I probably am. This is a 12 nanometer chip. How it compares. I don't think there's much out there, and because I'm using a WASM, there's no CUDA or any BS just-in-time compilers required. This system is completely sort of separate. Unlike the Google TPUs and the MPUs and things from IBM. I'm not trying general purpose. What let me be blunt about what like Google are doing with TPUs. They're essentially trying to create a kind of optimized inference system, or maybe a highly targeted like training algorithm. So it does that, but it's kind of broad. It doesn't really do anything beyond sort of taking what someone already has and sort of giving it making it a little bit faster. It doesn't learn. It doesn't adapt. It doesn't do the spiking neural networks particularly well. Like they've got a rudimentary sort of implementation from like 5 years ago when they made the chip. The chips are really expensive and they're not capable of being different things. There's no WASM, right? They're just once they're made, they are what they are. If I want to repurpose this entire chip to do something particular, DNA versus industrial control system, all I need to do is get the key and update the WASM, and now it's suddenly a DNA analysis, or now it's suddenly a industrial control system for nuclear power plants, like we did last week. And that's a matter of updating a WASM. So you can do all kinds of crazy stuff with that. All right, so that's coming in March. I'm excited. I'm excited. You can tell I'm excited about this. So, as you guys know, I've been building the RuVector system. So the RuVector system is, and I did a Postgres database for those who are interested. This Postgre, I guess they were telling me Postgre. I don't pronounce it right. Someone told me. But anyway, Postgre, and you can grab the Docker. Yeah, your question?
Can you
Sure.
show the specs for that chip again? You kind of passed through it real quick where it showed how much RAM and flops. Yeah, like chip level specification.
Yeah, I didn't share. I'm not sharing too much of the architecture. Obviously, I'm a giving guy, but this is a high level.
Okay, thank you.
Yeah, in fairness, Roger is, and I don't know if you guys have met Roger, but I called my last thing Tiny Dancer. He would be Bernie Taupin, I guess. I'd be Elton John, maybe. And he's the hardware guy, and his background is in building the supercomputers for a company called Silicon Graphics in the 90s. So, very experienced guy, and one of a dying breed of hardware folks. Most computer scientists these days are focused on building, mobile applications and websites and BS. He's from the school of, building in 7 kilobytes kind of school. And he's been showing me sort of the inner workings of these things and how you do it. And I've learned an immense amount about these chips. And you can, if you know anything about chips, you'll see the influence in the stuff I've been building over the last few months. They're all, and the Rust and all the things I'm building are directly influenced by that work. And so I'd actually like to get Roger on here one day. I think you guys would all appreciate his point of view. He's a great English chap. All right, so we've got the self-learning. So this, back to Michael's example earlier. So I created a WASM. This is not super. This entire WASM is I think I don't know the exact number. I think it's like 150 kilobytes. But this is meant to show all the capabilities. Tomorrow I'm giving a presentation to a gigantic software company, and they called me up and they're like, how in the hell are you doing this stuff? Like, it doesn't make any sense. At first we thought it was total BS. Then we tried it and it worked, and none of us can figure out how this random dude is able to do this stuff. So as part of that, I'm going to present this tomorrow. So just to be a kind of jerk, I want to show them something that doesn't require the cloud. And my story is basically, nobody needs your cloud. So my wife said I was being an asshole, but anyway. All right, so that's what's meant to do. So you can see here, I created some simulations. So we can go in here, we can see the vector. So we can go in, here, let me show you some of the settings. So I can define, so this is running, this connects to the local WASM. This is running in your browser, so I'm borrowing your compute capacity. We can change the dimensions. Keep in mind, when you're working with high dimensional data, the lower the vector, the more performant it becomes, right? So if you don't want to spend a bunch of money on using embeddings like from OpenAI or whatever, you want to stay below 384. And we talked about this a little bit last week. And so I set this to 128, and this is nice because I can use hyperbolic and other sort of structures. I can optimize for the lower dimensions better, right? Because it uses that circular thing I was telling you about. And so you can play with these settings. You can see the number of vectors and vector search and different options here. So now we're going to go in here, and I'm just going to, you can see I've included the Neo4j Cypher. I've got Sparkle for my old buddy Kingsley. By the way, Kingsley, he's the guru of ontologies and what he called the semantic web. So he sent me a note the other day and saying, man, you did Cypher. What's wrong with you? You got to do Sparkle. So Sparkle is his specification. So Kingsley sometimes shows up on these calls. And if you're on, speak up. But he's OG in the semantic world. What we used to call Web 2? That was the original meaning of Web 3 like 15 years ago. And then the crypto bros took it over. We got SQL. You can execute different commands and whatnot. We got learning, so that this supplies different learning systems. So we can train the GNN. We can see what's happening. I'll go in here in a bit more detail and explain what all this stuff means. But the most exciting thing, this is something Nick mentioned earlier, was the ability to do simulations. So this in essence is attempting to show all the stuff I was showing you on that chip in a kind of UI. And I could pretty much embed this on the chip. Again, this entire thing is 100 kilobytes. So it could be adjacent, like on a flash disk or something, like a thumb drive. And so this is giving you different settings. You can do the different simulations, embeddings, and history. But what I'm going to do is I'm going to actually do a supply chain. So what the supply chain does, this allows us to look at complex weather, and so as we go into the winter months, the ability to get resources from in a supply chain becomes complicated because basically weather. What this does is simulates all the different types of weather that could potentially impact the supply chain. So I'm gonna crank this up to 5x to make it faster. I'm gonna start the simulation. Now what's happening, we can start seeing that there's different things that it's starting to simulate different regions. Northeast, Southeast, I chose all. We're creating there's different types of options, and I can get more granular. I could say hailstorms versus heavy rain or severe, but I'm trying to show the art of the possible, so it wasn't that important. So he starts looking and so this is what it's sort of simulating. And I can cryptographically verify each one of those simulations using my favorite ED2551 spec that does millisecond or less cryptographic verification. Then I can trigger tests. So you can see here my activity log. I just triggered a remediation. So when we scroll down here, we can see the different disruptions that are happening. So these are doing a real-time simulation. So imagine the chip is just simulating what the potential risk factors are for delivery of certain food items and other things within the sort of supply chain. Then we got this idea, okay, how do I solve these problems? So these are sort of the AI generate remediation. So it's discovering and saying how we should handle transfers and adapting the different sort of supply chain demands on the fly. Now what I'm showing you right now is not running in the cloud. It's running on my computer. It's running against the computational resources in my browser and doing all the self-learning on 150 kilobyte WASM. So now we can see that's generated 53 nodes. There's 43 relationships, and I can go and I gotta fix up the UI for tomorrow, but we can execute that. When we execute it, we can see it's now doing a remediation based on the execution. I can take a look at the supply chain. The supply chain showing me different warehouses and how much they're full. It's created an entire simulated world of this hypothetical global grocery supply chain for an unnamed company, and it's showing me it's redoing distribution routes on the fly. It's learning, it's adapting, and validating. So now I can run. Now based on that, I can train a GNN based on everything it's learned so far. So I'm going to train that and get 93.6% accuracy. So I could probably run this a little bit more. So I'm going to run this again. So now it's running some validation tests to sort of validate that it's working. And here we go. So now we're seeing number of stores change. So retail, the distribution centers, we've got different routing components, disruptions. This is important. Stock out, the stock being out of not enough around, and potential savings. Now, if I can save a global retailer $243,000 in roughly the 5 seconds it took me to build this thing and deploy this thing, you can start thinking about the scale of these opportunities. So now we're looking at, so what do we got here? We got RV Lite. So I've demonstrated my SQL, I've done the Cypher, I've done the Sparkle, and the root vector GNN capabilities. And let's take a look at the statistics. We've got total warehouses 10. We've got total inventories. Oh, it's still running. We can see it sort of the numbers changing. So it's constantly running. I think I need to fix the problem in my console, but we'll take a look at that anyway. Yeah, I got some console issues. Well, it's not quite ready for main time, but I'm going to publish this later today. Actually, I might have already published it. I don't know.
Roof, can you do like a stack dump of this? Like, how is the data flowing through this system? From what you see on the screen and what comes back up. Because I think this is
It'd be cool to see like activity monitor, task manager too, to see what memory and CPU it's using.
I can get all that. I'm still working on it. You guys are so maybe we'll work on that here in a minute. All right, so I chose the export to JSON, and I'm gonna pop that here. And then what I'm gonna do is I'm going to rename that to text. And again, I'm still building it, so there might not be anything in this. We'll find out in a second. But so we're gonna go here, and I'm going to. I got too many screens. Take a look what's in this. Yeah. All right. It's 34 kilobytes. There's something in there. All right. Notepad. This text file is 7 times bigger than my WASM that I'm putting on the chip. Just FYI. All right, so let's see what we got here. All right, we'll call it RV Lite export. What was it? RV Lite. By the way, everything you're seeing with RV Lite is going to be the basis of an updated Claude Flow. So I'm replacing the data set structure with a WASM-based WASM structure. So it'll be using that natively in Claude Flow. JSON, there we go.
What's the inherent benefit of that, Roof?
Infinitely smarter. All right, so this is the raw data. All right, so let's see what we got here. We've got vector. So these are the vector outputs. These are entries. So this is the vector sort of location, essentially, I think. Then we got doc5. I think doc1. Okay, this is the sample data. So what I need to do, doc3, yeah, this is sample data. So what this data is actually, so I need to do is I need to update the system. I can already tell. We need to go to the system. And so when you go in here and you choose load sample scenarios, it's loading sample data. I think the export isn't actually, I think it's exporting this data. I gotta confirm. Yeah, so you can load sort of sample data to test the system, semantic search demo, e-commerce, company, knowledge base, movie, the graph recommendations, obviously from their hackathon this weekend, semantic web, and then a kind of complete demo. But let's keep looking here. What else we got here? So you see I'm using 128 dimensions. It's pretty good for this sort of thing. I've done 384, but it's a little more taxing and slow on the system. 128 works pretty good. That's probably what I'll end up using for Claude Flow as well.
Dimensions of what?
The vector dimensions, the higher dimensional structure in the vector. So rather than 384, I'm just using lower dimensions. Lower dimensions are faster. Remember, the dimensions with a vector are exponentially more computationally heavy the bigger they are. So 1,580 something vector, dimensions isn't actually 1,500 times more than one. It's like 15 to the X whatever more, right? It's not linear. So that's why 128 is so much more efficient than like the OpenAI 15 whatever. And it makes you think. I'm not really sure why they end up going with such a high dimensional structure for their embeddings.
Oh yeah.
It's almost like it's almost. Oh, I'm getting some.
Hannah is hot mic there.
It's almost like I think they want. It was like a business decision early on where like if we create some stupidly high dimension, then people are going to be stuck using our API to do the embeddings to train our models and things or fine tune our models. I think it's just another one of those evil OpenAI decisions. I think they did it based on money, not on practicality. Because if they did it on practicality, they would have chose a smaller dimension. But
so the high dimensions was to support a wide alphabet of tokens because they need to support the entirety of Unicode.
Yeah, they're all selling infrastructure.
Maybe, but when you're doing a fine tuning, you're at least if you do the type of fine tuning that I'm doing, they're not doing micro lowers. To the point, yeah, Jed's point's probably true. They're blasting the damn thing, and I'm doing micro updates to the thing. And so because I'm doing targeted precision surgical insertion, I don't need the large embeddings. I don't know. I'm just guessing. All right, so this is
a string using the O200K tokenizer. Would these SLMs be able to support it?
Oh yeah. I can do them. They'll be slower, but yeah. Your competent. Most computers are way more than enough capacity to do this. I'm just trying to optimize it. So when I looked at it, I'm like, how can I make this faster and smarter and more capable? And then being 384 ended up being the kind of magic number. And for browser, I'm like, oh, I'll just half it. So this is all the structure of the different properties for the simulation we saw. So it was doing the simulation. I was wrong. We've got here the edges. So this is the hypergraph. So this is the sort of to and from. So remember, I'm not doing a bidirectional graph, typical sort of graph. I'm using a hypergraph, multiple dimensions in multiple different directions, and then I'm applying that attention on those different edges. So these are the edges. Supplies, we've got. So this is what the simulation is running. Mostly supplies. And mostly we get store, we get warehouse, we get store, a lot of stores. It's simulating people, warehouse, stores, company, stores, a lot of stores. So it's basically simulating stores across the country and supplies that flow to them. Here's works at, supplies. I didn't tell it, it figured all this out by itself, by the way. I gave it a broad instructions. Remember, no cloud. This is all just sitting in a WASM, being go figure it out. Nose. That's an interesting one. Then we've got, this is Sparkle. Thank you, Kingsley. This is the injected data. So this is demo data. Yep, demo data. Yeah, okay. So it's not fully updating. I gotta optimize this more to use more of the data that's training as part of the export. It's only exporting a subset of the data, not everything. So I'll need to update that.
Are you persisting data between browser runs on this, or is it?
Oh yeah. So that's, yeah, check this out. Where did I put that? Save the browser. So what Save the Browser is doing is I'm using IndexedDB, which is the HTML5 or whatever persistence layer that stores the information directly in your browser using IndexedDB. Yeah, so I can persist all of it. And you can see the IndexedDB available right here. Save state found, and this was 4.6 kilobytes. Because I've used the compression system that I've also has that does the episodic compression. So because I was running it in hyperspeed there, it was basically simulating multi-day compression. So the newest stuff was compressed, the oldest stuff wasn't. So we can go and I'll crank it up to 5, and then we'll validate. And no, after here we go. I gotta fix that performance metrics too, I think. We'll update that. Yeah, so yeah, it's being stored locally in your browser. And so if you came back to it, it would reload it again. So we ended up creating 85 nodes with 66 relationships. We can query those. How do I got all persons? Well, I'm not sure why it's not working. It's probably a bug.
Hey Ruth, with all the stuff you're doing on the local machine now, is it fair to say that you've progressed from being the cloud guy to becoming the edge lord?
Yeah, out of spite. Yeah, out of spite, I think. Yeah.
The industry constantly toggles between that, right? Cloud-based to edge to cloud to edge. It goes back and forth.
I've comfortably cracked the edge, right? And I'm not saying that lightly. I don't think I'm living in a delusion. I am living in a delusion, but I'm aware of my delusion, which is one step away from pure insanity. But the reality is the power of these systems, whether it's in your browser, whether it's in a mobile app, whether it's in my chip, is in the collection of these things working in parallel in unison. Imagine what this looks like when you have TikTok embedding a WASM and having every single one of their mobile applications aggregating the capacity of every single user of their system in real time, low latency, quick backplane. Imagine when this is in, every light bulb sold, right? And suddenly every light bulb in every light on the planet is part of a broad neural network, right? And you start thinking about the collective power. There is no GPU on the planet that can basically compete with that. Now, what we suffer from is this idea of Jevons paradox. So, and I'm aware of the paradox. So for those who are not familiar with Jevons paradox, it's this. I'm gonna butcher the interpretation, but basically it's this idea of efficiency gains. So back to my chip for a moment. This thing is a million times less power, than a comparable H100, right? And I can put in a 1U rack, I could put roughly I would say comfortably 8,000 of these things in a sort of dense structure times 256 cores. I'm gonna just brainball the math on that, and that's what, 2 million or something cores. So 2 million cores on essentially 1,000 watts. So 1,000 watts. Let's crank it up a notch. Let's say 1,500 watts. So give or take the amount of energy that takes you to do a bag of popcorn in the microwave. And then so now I can do that, and that would cost, let's say it's $10 a chip. So $10 times 8,000. So you're talking $80,000 for 2 million cores, right? So that same structure in a GPU cluster would be $80 million. Yeah, $80 million, maybe more. 80 million at least, and would be probably less performant for most of the things that we're going to do in the demos I'm showing you. Now, when you start thinking about that, so I could do, and now you start thinking about that globally, and you've got a, let's say some astronomical amount of light bulbs. Let's say, I don't know how many light bulbs are sold every year, millions or like hundreds of millions. So let's say 100 million light bulbs have this thing in it. Each light bulb has just one chip, 256. So that's 2 billion. That's yeah, 2 billion chip. 200. No, sorry. Let me. 100 million chips, 256 cores. 20 billion. 25.6 billion cores. Yeah. Someone check my math. But all running in unison in a shared hive mind structure globally with a combination of highly latent, eventually consistent, interconnects, meaning that you turn off a light, it doesn't affect the overall swarm or the overall network itself. Learning, adapting, doing whatever it needs to do. That is the future, I think.
And that's not a big data center investment like we're doing right now.
No, that's you and I buying light bulbs.
How would state be maintained across the network? It can't, right? It's decentralized. So the expectation is
UDP.
a node that is 5 hops away will learn of the news later than a node that's 2 hops away.
Exactly. UDP. That's the beauty of the QUIC protocol. It assumes that architecture. It assumes the eventual consistency of the network. And the system is capable of much like when you spawn up my swarm in Cloudflow, they communicate with each other. They adaptively understand where and what. So I can create, hubs for a hive mind, which provides that ability for it to collectively understand. I don't pretend to understand how the hive mind works, but it does.
Something like 90% of the requests that we send to these huge models that can only run on cloud instances can be done by small language models. They were talking about that a lot at NeurIPS, and we're sending stupid stuff to a board of PhDs.
Exactly. And check this out. So first, everyone's like, well, I need my language model to work. So I'm like, sure, let's do that. So this is all built on that. So we got Ruve LLM. So the Ruve LLM architecture takes all the things I just showed you and creates micro LoRa's. This is probably up Jed's alley. But the micro LoRa essentially does really targeted sort of parameter updates and using these kind of tight little loops to do just the little piece that you need to do. So rather than brute forcing the fine tuning of the model, it's made every one that touches the model, be it a hive mind or users on your website or whatever, the system is potentially optimizing itself. Now it's optimizing itself in a couple different ways, right? It's optimizing itself globally, saying, what generally do I need to know without sharing the personal identifiable information? It's using the obfuscation and security parameters I put in place that basically strips out, and you saw that a few weeks ago that I demoed, but it's also working on a per agent level or per user human level and saying what's important for that particular user as well. And so you might train a language model that exists just for an individual versus a broader language model that might act as the arbiter of the overall swarm, and updating that and using that as a kind of episodic memory, which is where most language models are static in nature. You train it, it is what it is, and it never really does much more than that unless you happen to fine tune it, which most people don't do. Suddenly you take this crappy little neural network, 50 megabytes in size, and you're saying you don't need to be smart for everything. Actually, you can be just as stupid as you want. And I'm going to train you to do this thing really, really well. And I'm going to segment that all over the place and create different segmented things that you're super good at understanding and knowing and communicating using language. So
I think one of the biggest problems in AI right now is we're not giving LLMs big enough tools and letting them build big enough tools. Like they should be building these models when they need them. And that's a sign of intelligence. Can it adapt, generalize, and build and use tools?
Yeah. Yeah.
So-
And look at the speed here. So it's doing these micro updates, and this is using SIMD, but yeah, and these are real. Like I ran this many times, and I did on Kobe's Mac they got there, and the stuff checks out. The Sona learning system. This is how it learns. The Sona system's pretty cool. I'll show you guys that in a minute. We got the different, federated. The federated part, you guys saw me build that a while back. Then that federates using the quick and some of the federation sort of orchestration components. You can see it in my Agentic Flow system currently. If you want to try some of this, actually, I updated Agentic Flow at alpha. It's using RuVector, and it's using the federation it's using all this stuff. It's all packed in there in a tiny little WASM.
And when are you going to get that into Claude Flow?
I'm going on vacation next week, and I'm thinking maybe that's a bad time to do an update because everyone always I have a tendency to break stuff, and then I get those 1,000 message mornings. In some weird way, the 1,000 messages makes me feel like I'm doing something meaningful, but it also stresses me out. Right? Some of these guys are so mean.
We get that.
Yes.
Well, just know you have an awful lot of people looking to see that hit. So
you guys can all
whatever you can.
You can use it today. All you need to do is just use Agentic Flow at alpha. Point Claude at it and say use this instead of Claude Flow. Done. Okay. So you're going to update
RuVLLM part of RuVector?
Yeah, it is. It's all integrated. And there's a Docker image for those who want to sort of, get up running fast. All you need to do, actually, I've got a few things you might want to check out. This one is the Postgre. That is everything loaded into the center of the Postgre database. So everything I just showed you exists as a drop-in replacement of pgvector. So basically, it infects your database. RuVector is the sort of core. This one's kind of cool. These two use. I basically borrowed the Supabase open source UI. Like when you use Supabase, this basically replaces Supabase with RuVector and looks just like Supabase. It's kind of a cool feature.
And why would we want to do that?
It's pretty UI. Everyone always complains about my UIs. You get the Supabase UI and the RuVector insides. So, and you can call all this stuff, by the way, using SQL or Sparkle or triggers or other sort of Postgre sort of inherent database structure. So every time you save a file or save something or access something, the system is literally just learning, and you just add that as part of your sort of trigger to that particular function you're doing in your data set. So it just and because it's so fast, it adds zero latency to your database because I'm working in microseconds. The database is working in something in orders higher, like milliseconds. So I'm injecting it faster than it operates, so you don't notice the difference. Yeah. So let's jump back here for a sec. So that's RuVector. The best model, I've trained this on a whole bunch of different models at this point. The best model I found, there's two that are I find if you're looking at reasoning, the Gwen 1.5 is amazing. And that gives you reasoning. If you don't care about reasoning, then you're going to want to use the Gwen 0.5, and that it gives you an instruct model. I typically use instruct because a lot of what I'm doing is kind of instructional. I don't really need it to reason on this stuff. I think there's a whole thing we can explore in the reasoning part. I haven't dug into that too much. But right now, most of the things, like if you're creating like an industrial control system or you're doing like a legal analysis things, you just want it to be instructed. I'll get Claude, 4.5 to think. I'm good there, but I want this to do. And instruct models are really good at doing. Use this tool. Now, the next part of the equation, which is interesting, and this is becoming one of the more popular parts of this whole package, is this idea. It's in crates. Where I gotta find it, is TinyDancer. I mentioned this like last week. So I've got two different routing mechanisms, and I'm using this also, for the chip-based routing. You're kind of getting a vibe for where and how I've kind of architected the chip by just looking at this project. But what this does is provides a ability to really quickly understand where and how the requests need to be given. So when you think about a larger swarm, the question is, what resources do I need? What AI should I use? This allows you to do feature extraction in 144 and maybe faster with the chip, probably point something nanoseconds, and determine where and how it needs to go based on this. You send a request, it sees candidates, the Tiny Dancer scores the candidates in microseconds, and then gives you a confidence, and then sends it to the more expensive model, a certain GPU or a certain core within a cluster, whatever it needs, and it figures out where and how it needs to allocate those things. So someone was asking, like, well, how does it know how to communicate? It's doing that because I've applied this concepts of a fast GRNN. You know, it's like, what the heck's a fast GRNN? So the fast GRNN, let me see if we can find that.
Hey, Rube,
Fast
did you take a look at Samsung's tiny recursive models, where they're doing
No,
like a
I
7
should
meg
though.
reasoning model that outperforms the cloud reasoning models?
Oh, I should totally look at that. You said 7 megs?
Yeah, I
Oh, you gotta send
posted
me
a
like,
link. It's crazy.
yeah, where's that? Oh, let's take a look. All right. Oh man, you guys. All right, let's do it.
I
All
think
right,
it's
so I'm
7
gonna.
million parameters, not megabytes.
Okay, well, that's still tiny.
I agree.
7 million? Yeah, it's 7 million. It's probably 7 megabytes. It's gonna be tiny. Okay, there we go. We're gonna go with this one here. So now we're gonna vibe. You guys are gonna get me going. We're gonna create something crazy, aren't we? I gotta find my right. I got too many things open again, don't I? Right.
Earlier, you mentioned a bunch of LoRa's, Roof. What are they running on top of? Because LoRa is a low rank adapter, so
I'm using
it's like
Rust.
putting a lens in front of a light.
Yeah, I'm using Candle. I think I gotta get back to you on that. I'm using some Rust libraries that handle the LoRa. I was lazy. I don't rewrite everything. In this case, I just found the optimal Q LoRa, and then I dreamt up this thing called a micro LoRa, which basically, maybe a micro LoRa is a thing, I don't know, but basically the micro LoRa just does the Q LoRa process in microseconds, basically sub millisecond sort of time increments, which I say just casually on a Thursday call, which in itself is probably would have been like the height of IT like last year kind of thing. All right, so here we are, Rue Vector. All right, so where were we at here? So where should we put that? I think that should be. So I'm gonna create a new. Actually, I'm gonna commit all this first. DSP. And there's an update to Claude. It's pretty nice. And now they separate the agent stuff into sort of separate threads, which is nice. All right, commit everything. Actually, I should probably create a PR on this. Maybe to branch and create a detailed PR. Sorry guys, it's gonna take me a second to do some housekeeping. But while we do that, what I'm gonna do is I'm gonna ask some questions. Review that site and how can we use it with at Rube LLM? You know, give me a practical overview in simple language, including benefits, unique capabilities, speed, and other use cases. I don't know, something like that. Just I'm gonna go full ultra think on this one. You gotta ultra think it. Ultra think enabled. All right, let's go back here. Sparkle. Yeah, if you guys don't follow Kingsley he's active on LinkedIn. If you're into ontologies and semantic web, he's the guy. He's basically invented the space. Really
That's
cool
awesome.
guy. Yeah. I love these things where someone randomly sends me a note and saying, you should do that. I'm like, all right, let's do it. That was Michael on the WASM I think we hopped on a call there. I think on over the weekend. It was like middle of the night or something, and he's like, we just riffed on this, and then we ended up creating that WASM. That is in. But if you want the mobile one too, where is that? Sorry, you get a comment?
So I just attended NeurIPS last week, and probably 6,000 different papers, but it'd be an interesting research topic to go and have your deep researcher look at all the papers and determine which ones might improve any of your frameworks. I'll send you the ones that I think you would care about, Ruth, but
yeah,
I think it'd be a great deep research project.
Guy, archive is programmatically accessible, so just have Claude Code go through it and then compare it against the repos.
Yes,
Yeah.
that's usually what I do. Oh, here it is. I got too much crap. Okay, I don't even know where half this stuff is. Okay, it's in examples because I got so many freaking things. It's getting a little messy. I got to clean up here. Examples, WASM. Here it is. Yeah, so this is the mobile one. For anyone interested in the mobile stuff. So this is the privacy preserving iOS. So this WASM is optimized specifically for iOS data. So it's single base for the iOS and browser kit. So there's a WASM kit available for iOS and browser, so you can gain access. I've got the HNSW algorithm. I use Q-learning. We did this quickly. We could probably add more. I think there might possibly be more, just not documented.
Is there an
SIMD,
Android version too?
no, it'd be relatively easy to do. I just don't have an Android handy.
Okay.
Point it at my repo and say, create a WASM / Android. Q-learning, we got SIMD again. SIMD is the trick to all this stuff. So make sure you enable the SIMD on any of this, and you get exponentially better performance, like 1000x kind of thing. Here's my memory efficiency, self-learning, health, location, calendar, app, and usage patch. So yeah, I've got direct integration for these. So if you're creating a Vibe app like what Michael created, right, or you want to create a health app that monitors whatever data you're getting, this could also work interestingly if you are like diabetic and you're using one of those apps for tracking your your glucose and whatnot. This would also work, which would be cool. So you could start hacking your own data. Yeah, private. So it never leaves. No one sees it. It's completely anonymous. Stays on device. It's encrypted, unless you save it as a JSON, then it's not. But you can completely encrypt it if you want to. I'm sure that someone at the border somewhere will want to see your biometric data at some point. So use my encryption. Yeah, here's some. By the way, this whole thing that I'm showing you here took 10 minutes to build. It took longer to do the WASM build. When I say build, it took longer to do the WASM build of the actual binary than it did to create the code to create the binary. Which is amazing, right? And it's a lot of stuff in here. This is what 10 minutes looks like. This is the WASM. Is there size in that? No, this is the WASM. This is what you need. You can rename that depending on the environment. The WASM is just an arbitrary name, but it's basically binary. Here's WASM vanilla. I got other WASM examples here for you guys. And if you are interested, if you're looking at doing this sort of thing, I've also got a super lightweight. Where the heck did I put that? A super lightweight micro. So what this is, I don't remember exactly how super lightweight I made it. We'll find out here in a second. Yeah, so this is a 7.2 neuromorphic core. So 7.2 kilobyte core. You could put this thing in pretty much anything, and it'll give it a neuromorphic core. At 7 freaking kilobytes. I've been really on this kind of micro. I'm sort of playing in the space between temporal dynamics, speed and time, and size. So I'm both shrinking the informational size and grossly accelerating the ability for it to do these things really, really fast. So this is looking at that. So I've included a spiking neural network. I've got a graph neural network. I've got vector search. I've got, and by the way, each one of these things you're seeing, boom, back in that chip I was showing you guys earlier, 7.2, right? It's under the 8 kilobyte range. So what I'm thinking also, maybe I'll create like an app store or something for the chips, and we can hack different use cases that we can embed. I'll show you. You can figure out how to do it just by looking at this folder. Just say, build me something crazy small. And by the way, when you're quantitizing these systems, don't do it all at once. Start bigger, and then test the functionality. Make sure it works, right? You don't want to quantize before you've tested the functionality, because then you got to decipher where it broke, right? And that's a pain in the butt. All right, I'm almost done. I'm almost out of time here, so let's just see what this is. Okay, so this is back to the tiny recursive models. This, in plain English, TRM is a thinking in loops approach to AI. Instead of using massive parallel and billions of parameters, uses a tiny 7 million parameter model that thinks about the same problem multiple times, refining its answer and iteration. Sounds very similar to what I'm doing. How TRM works in simple: start takes your question and plus initial guess, runs through the model. Each loop has 2 parts: thinking, refinement. It's doing the same thing I'm doing. This is my Sona model. It's doing Sona. Ruve already has, oh, here it is. Ruve already has Sona self-optimizing neural architecture with 3 learning loops. TRM's recursive approach fits perfectly. Okay, that's good to know. Integration points, micro LoRa's, TRM recursively layers become learnable. Reasoning bank stores fast GNN layers, routes queries in one loop. Prevents forgetting, EWC, graph attention. Runs 99% fewer parameters at 80% performance. Giddy up. Speed, it's effing fast. Roof's HN finds similar paths, so I'm crazy fast. I've got edge deployments. Roof can better decide how many TRM loops to run. We can do learning from recursion. Federated. Oh man, guy, you're the guy. All right, we're gonna do this.
So what are we gonna see next week when you come back and you've had a week to play with this?
Yeah, no,
Nothing,
we're gonna have
because
this
he's on vacation.
Well, yeah, you want me to, yeah. Okay, so create detailed implementation plan in docs subfolder using Spark for the TRM. Include attribution. And that, when I say attribution, I'm really saying fuck you, Linux. But anyway, include attribution and details of the next version of Roo LLM with benchmark, optimize, and prepare package for release. Something like that. All right. I'm going to do one more thing before I do that. I've created a new branch. That's good. I created PR. So I'm just going to create, what am I going to do? I'm going to say create new branch, update frequently, because I'm sure you guys want to watch, and update, commit frequently, and prepare package for release. Yeah, so that looks pretty good. There we go. That's it. It already knows. It's already in my repo. It knows everything it needs to know. I've got a self-learning system powering the whole damn thing, right? I don't really need to tell it much. I told it to do Spark. So this is going to do it. This is going to be crazy. Browser extension, WASM. I can run the whole thing in a WASM. There you go. I can get this smaller than 60 megabytes. Way smaller. Don't worry about that. This is a great approach. All right, that is it for today. Last week I like daydreamed and we ended up missing my meeting. But I won't do that. I won't do that this time. Where the heck did my...
Thank you,
All
Rune.
right,
This
guys.
was great.
Yeah, that's it. That's all. Weird week.
Thank you very much. It was my first
Onward.
meeting. Very nice.
Oh yeah, good to see you, Mario.
Thank you.
You're gonna need a cigarette.
It's a lot, right?
Some time to process this.
Roughly 500 million cycles a second to process it.
Yep.
At least if you're using my chip anyway. Exciting times. And by the way, just to make sure, everyone that's on these calls in the tribe and I'm gonna try to get you guys as the first to get these chips. I want these to be ubiquitous. I'm not going to charge $5,000 a pop. I'm going to make these things cheap and plentiful. You know, take that, tech industry. Anyway, that's it for me. And again, I'm going to say it again. Thank you everyone for the support this week. You know, you guys really did support me through it, and I really do appreciate all everything you do for me, and I'm honored and happy holidays. All right.
We appreciate you, Ruth. Thank you, Ruth, for everything.
Thank you.
All right.